All right. Yes, there's going to be a test 5, which is largely hashing and there's a few concepts. So the final. All right, so last test. All right, so the final's on the 20th. So the last test will be either the Monday before or the Monday prior to that. Let's see, when is the 6th relative to today? The 6th is in 3 weeks, maybe. So either the 6th or the 13th will have test 5. All right, so you see I have it here tentatively on Monday the 13th. It's probably when it will be, but if we finish and are ready for everything, then we can change the dates accordingly. No, test 5 is not the final. The final will be on the 20th. Right, and the final is comprehensive. Test 5 is focused on hashing and memory operations. Is there extra points of opportunity? What do you mean, are there extra point opportunities? There's nothing outside of the assigned items. Let's talk about program 4 while we're here. Let's see. Program 3. I believe we went over that already. Try to confirm if my memory is wrong or not. We went over the trees and the levels, a lot of good stuff. Okay. All right, so back to, remember, so the sections in the whiteboards, right? The first digit is the test area, right? So test 4 was graphs, test 5 will be most hashing good stuff, and then other items, and then cumulative is final. Yes, so each test will be 12.5%. There are 5 tests, lowest is dropped, and that's 50% of the grade, so each test is 12.5%. All right, and Canvas should already be reflecting the lowest score being dropped already. And I colors it for me on my grade book. I'm not sure what it shows on the student view though. All right, back to the last item we were talking about. All right, deleting from the hash table. Any questions about having to account for the empty position so that our lookup does not get compromised? We want to still be able to find the data that we're looking up. The whole purpose of the hash table is fast data lookup. Little X next to the drop test. Good. I figured it showed. I just didn't know how it did it. Okay. Next topic for test 5 is going to be garbage collection. All right, so some programming language runtimes have built-in garbage collection. Garbage collection is reclaiming dynamically allocated memory that is no longer needed. All right, so for example, object O equals new object 5, for example, and then we just say O equals null sort of thing. All right, so the object 5 is no longer accessible, and it is garbage at this point. There is a built-in garbage collector. May be able to reclaim that memory at this point, or at some point in the future. If the language of the runtime does not have built-in garbage collection, then it's on the developer to manage that memory themselves. All right, so right, if we have some sort of linked node, star node equals new linked node 25. We say node equals null, and this being C++, this is going to give us a nice memory leak. All right, so a memory leak is dynamically allocated memory, dynamic allocated memory that we no longer have access to. All right, so many of you have been writing plenty of memory leaks throughout the semester in your various submissions, because for every new keyword, you need to have a corresponding delete keyword, otherwise you're going to create a memory leak. One of the most common, all right, I commonly see an example. Say we have a binary tree node, or binary tree of whatever flavor. Binary tree node start temp, and people have a tendency to create a new node and then turn around and say temp equals root. If I can type, I'll type root, and then we have a memory leak. And so let me demonstrate. Let's see, drawing is what we're going to want to use here. So you remember way back in the beginning of the semester, talking about our dynamic memory. Hopefully we still remember all that good stuff. All right, we have two areas of RAM. We'll commonly find our variables. Got the stack. And then we've got the heap. All right, stack. One area, and then our heap in another. All right, so at some point in time, let's say, let's just go here. We created our root. All right, so we've got our tree constructor, tree class, added some data. All right, we have some sort of logic at some point. It said root equals new tree node, whatever it was called, and we passed along data. And that gave us our root object. Let's say the data was 22. Let's actually add the code. Tree add 22. So somewhere in the heap, we have 22 as a node. Somewhere else, let's say I just called it tree. Right, somewhere we have an object called tree. Inside the tree, there's a root pointer. That pointer points to this node 22. Right, and somewhere in main, a variable called tree, and that simply refers to our object in memory that we dynamically allocated previously. So when we come along and create a temp node inside a function, that temp node is a local variable. What did I say the value was? 25. Yeah, let's give a data point. Let's make it 94 just so we can reference it over here. And we'll bring the code over both places so we can see at the same time. All right, so we're creating temp, and we use the new keywords. The new keyword says create a box in the heap somewhere. Now we're just going to track it with the value 94. And then we set temp to equal to that. Let me move things around here so lines aren't crossing. Oh, that's nice. It's always fun when things fail to anchor themselves. Attach, please. All right, so that's one point in time. So let's get to the next point. Temp equals root step. All right, so the assignment operator says copy the value in this expression on the right-hand side. So root is saying 22. I guess I need another arrow here. Go by their drawing. All right, 22 was our root. So when we say temp equals root, we're saying to forget all about '94 and point to 22 instead. And in doing so, we create a memory leak for this 94 object. The object was created on the heap, and now you no longer have any pointers that can get to it. So in C++, assuming we're not using any of the newer language features that have built-in garbage collection, we're creating a memory leak. Questions about memory leak at the moment? I think C++ 11 added a library that you can add in there. Oops. To do it, yeah, C#, .NET languages, Java, Objective-C, they all have built-in garbage collection. C definitely does not. Right, you need to use the free keyword. So for C++, for every new delete, for C, for every alloc function, malloc, ralloc, realloc, well, not necessarily realloc, but malloc, calloc, you need to make sure you have a corresponding free. Reference counting, garbage collection. is one way to do this. Objective C uses this approach. For every assignment operation, we need to track the number of references there are to an object. As a new reference tracks an object, we'll go ahead and increase the count to that object. And we'll do the reverse. A reference stops tracking, stops tracking an object by decrementing the count. The count of references ever gets to 0, we'll immediately be able to reclaim that memory. All right, so again, so references are the pointers to the objects. Objects are the allocated space on the heap. Right, we don't have to worry about memory leaks on the stack short of a recursive function gone awry, because as a stack frame ends, that memory is immediately available for the next function call. So anything that's a local variable right, so as you, oh my God, as functions come and go, the stack frame grows and shrinks as they come and go. We don't really have to worry about those local variables. But if they are pointing to other variables, then we need to track things. Okay, so let's go ahead and have our little objects table here. And so we have name, references, and some code. And means this can be some pseudocode. All right, we just use the term object to represent some sort of object. Could be a tree, could be a node, could be a linked list. Doesn't particularly matter what the data type is, whether or not there's pointers here or not. Right, we're abstracting language away from the concept. All right, object equals new object. And we'll just call it alpha. And we need some, let's just put all the code here. We'll do states as we go. Now, we'll do some line numbers. Line numbers. Okay, line. Second object, new object beta. Then create an object reference third, but not actually create a third object. Just have it assigned to second. Then we can have first equal to second. And then we'll just clear everybody out. First equals null, second equals null, and third equals null. All right, so we have alpha come into existence with first tracking it. All right, so after line 1, That is all that we have. Right, after line 2, the second object is created called beta, and we have one reference to it, that reference being second. And might as well delete unused rows. All right, so after line 3, third equals second, right? Second has this location tracking beta. So now we're adding in third to also track that same object. So we have 2 references. So my count is 2. 2 references to our object known as beta. All right, line 4 says first equals second. Second is tracking the beta. At this point in time, we no longer have any need for alpha. Our reference count goes to 0. So we can immediately reclaim the alpha object. That memory is available for a future allocation if another object needs to be allocated while our application is running. Any questions about line 4? Right, so the reference count is stored in a table. Right, so there has to be a data structure that we're managing. Right, so the runtime has to keep track of these things for us, just like the runtime has to keep track of the heap. Right, the runtime has to keep track of where the stack pointers are. A lot of that's handled with inside like the CPU itself for like program counters and all other stack pointers and return addresses and things like that. But same thing is just like the variable names, right? So variable names are more than just their name. There's a memory address and the value at that address. And right, when we're writing high-level programs, those high-level languages have all kinds of internal mechanisms to maintain the state of the machine. And for the most part, we don't have to worry about those too much. But in this class, this is where we start talking about these things. So, right, if we're just writing flat assembly is not going to have a whole lot of all this fun stuff because there's not that high level abstraction of the details. So these reference counts need to be stored in an appropriate data structure so we can quickly go from variable name to its entry in the table. So we can go ahead and increment or decrement the count associated with that reference and then take an appropriate response when we need to delete from said table. So what data structure do we think of the ones that we know about we might want to use where we're going to be frequently looking up a value to get its associated data and increment or decrement that data? Any guess is fine. It's a 0-point question. Right? We could use the linked list. Linked list will give us some linear time trying to find any named data point. And then we've got hashing. Hashing ideally gives us constant time data lookup. Right? So if every time I have an assignment operator in my code, I need to look up that variable and move it over. The hash table looks to be good. And it's certainly good for now until we find someone better to do the job, because constant time on something that we plan on doing a lot is something we definitely want to be achieving, right? So we'll look to see what's the nature of our problem. Is there a constant time solution for the problem? If not, can we find logarithmic time, then linear time, right? Some things, sorting, for example, trying to achieve a linear time solution is theoretically possible, but practically not. Let's see, one of the solutions I've heard for right? Sorting a set of numbers. You just go ahead and create an array. That is the full range of that set of numbers. And you just go ahead and every value, you just put it into that location in memory. And then you're good. Problem is, practicality of 4 billion values that you might possibly have in your number range, the set of numbers you're going to sort doesn't work terribly well. And of course, if they're non-unique, then you have a little bit of a duplication problem. Okay. So carrying forward, as we start killing some references, line 5, right? So line 5 is saying first equals null, which just means it's dropping off the table. It's no longer tracking anybody. Line 6 is eliminating second. All right, so our count's not to 0 just yet. So beta continues to live. After line 7, count of references to beta goes away. And as soon as that state is identified, we can go ahead and reclaim that memory. Any questions about the states? Here's it makes sense. Another example in a moment here. So line 5 isn't first supposed to be removed. Did I get rid of the wrong thing? Line 5, did I kill the wrong thing? It's very possible I killed the wrong thing. Let's see. Who did I delete? Deleted third. So I got things backwards. All right. So third should still be around. Then we got rid of third. Thank you for cross-checking me. I managed to delete the wrong entry. Line 5. First equals null, so second and third are still around. Second's also, okay, there we go. All right. Let's add a couple of functions in here as well. Let's see, just call second there, call fun. One at that point. Make this a void. All right. Beta is going to be our first object. All right, it's after line 2. Beta gets created, exists. After line 3, we have the same state, right? Line 3 calls fun1. Fun1 creates an object. And then the stack frame that defines first goes away. So by the time we get to line 4, alpha has come and gone. Let's simplify this one. So we don't have first here, we don't have second. Should have third and second. Third equals null and second equals null. Right, so after line 3, nothing's changing. Because the whole stack frame came and went all on this one line of code. All right, so we have more embedded lines of code in here. So while we're inside the context of fun1, the object exists. But as soon as we leave the context of fun1, all the local variables go away. So all the variables that those were tracking, all the objects that those were tracking, they also go away. And we need to decrement our counts. Okay, so after line 4, we have third. In the equation. All right, line 5 then takes third out of the party. And then line 6. We now have no data. All right, so every time we have a assignment operation, you do some tracking. Tracking, make sure things are changing or not changing. Let's try to have some more actual code here. See if we can track things. All right, do a for loop. A loop, yeah, 3 times is probably good enough. Okay. Sometimes the references get capitalized, not capitalized. Part of it is just Google's automatically capitalizing things for me. And I try to correct that as I see it. Being that C# is my day-to-day, C# naming conventions is you capitalize data types. So I do also use that convention here for one of the reasons help differentiate object references as objects as opposed to data types. Just keep my data types capitalized. Right? It's certainly harder to see when we don't have color coding going on in here for us. Okay, so our objects. Our first object, let's say we're tracking a name for the tree. So we'll call the tree happy. So we have our happy tree. And it's referred to by our tree variable. After the first iteration of our loop, called tree add. So we now have this object 0 inside our tree, and the reference is going to be whatever. We'll just say it's tree, and it's going to be in the root. Yeah, we'll just assume this is a binary tree. It's just a flat binary tree. But inside there's going to be a root node. That root node is going to be no longer null. So initially, root was null. We added a node, and 0 is that object, and root is tracking that object. All right, so at this point in time, tree is alive. Tree is tracking happy. Happy has a root. That root is non-null, and that's tracking 0. So there's no garbage that we can find as of yet. And let's just say this tree just does a level by level building, right? It's a min heap. So the tree has a root, and that's left is going to point to our node 1 that we created, right? So we create another node every time we add a data point. And then object 2 gets created, and that's going to be on the right side. All right, so we're doing a link-based min heap, even though we should be using an array. At this point in time, everyone has a reference to them. Some of these references are buried inside of the object structure. That is our tree type. So when one line of code hits, all right, after we say tree equals null, all of these counts need to be decremented. All right, here's one of the complications of reference counting mechanics. That one statement of code setting tree equals null, all of our counts drop to 0, and we now have no garbage floating around in memory. Are we able to keep track of our references? Got our counts up, down, left, right? Increment from 0 to 1, and then 1 back to 0. That's our critical threshold. Things, the relevant work is being done, right? Just keeping track of the count is just the job. And actually getting the can empty is the purpose of this mechanism. We're still on Monday, right? We haven't rolled over into Tuesday just yet. Any questions at the moment? It's always fun to learn things after a test, right? It's one of the disadvantages of having the test first. Okay. And the other way is the more common way to collect garbage. So, tracing, also known as a marking, garbage collection. With this approach, at various points in time, we'll go ahead and take a look at the allocated objects and the means to get to them. We find that there exists one or more objects that are not reachable. Then they are subject to collection. and can be reclaimed. All right, so an object is reachable. There exists a variable or other memory mechanism such that we can find a way to get to that object. All right, so for instance, we have a binary search tree with 4 nodes. So long as we have either a local or global variable, it has the reference to the tree, all the nodes are reachable through that reference. All right, same idea. Any linked structure or hierarchical structure. I'm glad Google knows how to spell because I might have been here all day trying to figure out how to spell hierarchical. Okay. All right. So for example, say we have class page, and we have class whatever, author type things and book. Inside book, we have list of pages. And then we have our author sort of thing. So when we come along and say book equals new book, and presume that the constructor goes in, builds all these things, right? The set of pages that belong to that book and whoever the author of that book is, all the other sort of details are all accessible through our B reference here. So until the book goes away or someone rips out pages from the book, these objects are reachable, and we want to go ahead and maintain that we can find a way to those items, and we're going to keep them in memory because the program has the ability to get to them, thus we shouldn't get rid of them at all. Until that point in time comes where we say that data is no longer needed. Okay. So a sample marking garbage collector. The tricolor algorithm. This algorithm is going to separate all of the objects in memory into 3 distinct sets. There's a black set, black bulk, black set, gray set, and white set. Black set contains all the objects that are determined to not be garbage. In order for an object to get placed into the black set, it must not have any references to objects in the white set. Objects in the gray set, those objects that may still have references to objects in the white set. In the white set, are the objects that will be determined to be garbage or not. That's our initial setup. Black set is going to be empty. Gray set, these are our root objects, which includes stack variables, global variables, or anything that's in registers, etc. Items that are directly accessible. In the white set, all other objects. Our algorithm, try color, algorithm. Take an object from the gray set and blacken it by pulling any objects that it has references to from the white set to the gray set. Can then be placed into the black set. Repeat step 1 while the gray set is not empty. All right, and at this point we can go ahead and reclaim any objects that remain in the white set. Okay, let's create some objects. All right, so we have a tree. There's one of our objects. Go and create linked list. And just say that's a hash table. We should call it table. And let's create, we had that book before, so let's create that as well. All right, so we have a 587 page book. So I'll just call that my page list. And we have Bob Smith is the author. And all this is our it's back. Let's just say we have book is called Data Structures, first edition. Okay. All right, so given the above objects, the above objects in the root objects as F table and our book. The book determine which objects are trash. Right, so F, our table and our book at the top level have direct references to it, either as global variables or local variables, but they're directly accessible. So what we need to do is get our sets, or black set, be empty to start. Gray set will be our roots, which I define to be F table, and we'll just simplify it to saying in the book. And then the white set, all remaining objects, which have A, B, C, D, G, H, 587 are pages, and Bob Smith. Because when we went and created an object for the author, could have associated data inside it. That's still on that object level as far as we're concerned. So we're going to go ahead and take first object from Gray, which is just F. Gives us F. Need to look at our references. F has a reference to G. Since F has a reference to G, we'll need to move G into the gray set. So our first transition, right, we pulled processing F, so it's no longer in the gray set at the moment. Right, it's in transition, and we've pulled G out. Right, so G is no longer in the white set. As more of these sets are distinct, G cannot coexist in two sets at the same time. F is in transition. So our next state change is to put F over here in the black set. Right, it had just the one reference. We had to move one item out from G, from white rather, and into the gray set. So we now take, repeat, and take table from gray, has no references. So it just moves into the black set. Table gets pulled out of black set. And we're good. I guess I need to put quotes around this. I'm happy about my grammar. And again, gray is not empty. So we'll keep on repeating. And so we'll yield book. All right, so we want to take book out of the gray set and process it. Book has a reference to 587. So 587 leaves the gray set, and Bob Smith, also referenced inside books, that leaves the white set and goes into the gray set, and book finds its way into the black set. All right, we'll take G next. G has a reference to H. All right, G goes to H, so we need to pull H out. From the white set, after we pulled it from the white set, G is good to go. into the black set. We'll take 587, just like our hash table. 587 does not hold any references to anybody else, so it just moves on over. Brings us over to Bob Smith. Bob has nothing to pull from the white set, so it moves over. Go ahead and pull H. Also does not have anything in the white set. So it gets pulled out. All right, gray set is empty. So we'll stop digging. Now we can reclaim all the objects in the white set. All right, so what brought us here was at a time, or at a previous point in time, we had a tree with A as its root, but the tree reference went away and created a bit of a mess. And we just got around to cleaning up. Right? The purpose of the sets is to work our way through all the items in memory and figure out what's trash. Basically, all throughout the week, every time we stopped handling something, we just toss it in the closet. And it's Sunday night, and we were digging through the closet and finding out, okay, what did we toss in the closet that we don't need anymore, right? There's the candy wrapper. Okay, that can be pulled out of the closet and disposed of. And banana peel, right? A sock that's got too many holes in it. It's not worth keeping at this point. So we had to go through and find out what of all the collection of objects that we've been accumulating as we've been doing things, what's become trash and what hasn't become trash. And all the stuff that we have no further use for, we've discarded the references to them and they just got left behind and we just need to go ahead and clean them up. So the sets are what we use to track what's kept and what's not kept. So everything that made its way to the black set are items that are reachable. They are reachable because they were already root items. Right, so our root items, ftable and book, are immediately reachable because I have local variables that are still on a stack frame somewhere. And we've determined that they're still reachable and we want to keep them. Let's take this to a code example and try to demonstrate. All right, so we've got main. Say we have some sort of function. Build tree, builds up a whole bunch of tree. Tree calls print average, whatever it is. And then we say t equals null. And actually, we'll do this a little bit later and see if we have some sort of list. Groceries equals list. Groceries. Groceries, if I could spell, I can just go and copy paste. So groceries has some sort of function that says, print the list. And go shopping. And now, since we've done our shopping, we can go ahead and just set our list to null. And let's just say return 0, all good and done at this point. Okay, let's get some line numbers in here. What? There we are. Okay, so if garbage collection runs after line 1, T are root objects, T. All right, let's go ahead and draw out as well the various objects that could get created at some point in time. So we have a visual to work with. All right, so like before, we have our tree. Yeah, 3 doesn't get enough, you know, X, Y, Z, X, T, Z, whatever. And we have our shopping list, which is going to be array of linked lists. Not what I meant to do. Try that again. Try till you succeed. All right. Come on. And we got eggs, flour, cream, whatever. Plan on doing some baking. So after we found the eggs, we'll get the flour, we'll get the cream. Right, so these are our objects that our program is going to create as it goes through things. Right, so T, it's up here, it sets pointers in here. Here's T, and then groceries. Right, groceries is tracking that list, and T is tracking our tree. So we have our T root object. Right, so after line 1, this list doesn't exist just yet, so we're not going to worry about that. T is in the gray set. I want to blacken T, so I move X into the gray set. I want to blacken X, so I move T and Z into the gray set, and then everyone ends up in the black set. And there's no garbage at that point in time. In fact, I might as well just represent. We have this point in time, so that's a big. All right, so black starts off empty, gray is T, and then white are X, T, and Z. Next state, we'll have T moved out of gray by pulling X over. So we've determined X is not garbage at this point. We're going to keep on digging. I want to bring X out. Gray set, and to do that, bring over T and Z. Yeah. This is a bad name for that node since I've got called my tree T as well. So let's change that to Y. And X, Y, Z, X, Y, Z, X, Y, Z. All right, so Y and Z can be pulled out of the white set when X comes, right? X has a reference to Y and Z, the left child, right child. They get pulled out. And we can also just stop at this point because the white set's empty. We're not going to find any garbage, so might as well just stop processing. And so this is our processing after line 1. If the garbage collector, Right, runs after line 2, we have the same thing because nothing's really changed. So let's add line 3. After line 3, we have more root objects at this point. So root objects, T and groceries, right? These being just our stack variables. T exists, now groceries exists. We create our sets. Right, black starts off as empty. Gray is T and groceries. And then all of our other objects start off in the white set until we can determine if we can or cannot get to them. All right, so we have X, Y, Z, eggs, flour, and cream as objects that we want to find out if they're garbage or not. And so our final state, after running through all that, we will see that the black set has T. We pulled groceries over as well. Right, when we pulled T out, that brought X into the mix. We brought groceries out, that brought eggs into the mix. And then X brought Y and Z. Eggs brought flour, and then cream. Gray set was emptied, and the white set was emptied. So there's also no garbage. All right, after line 6, and go and grab line 6, which says groceries equals null. It's the same as we just had, except we've lost a root object. So this groceries list is no longer relevant because we've already printed the list out. We went and did our shopping, and we can now discard needing eggs, flour, and cream at this point in time. If it's information we no longer care about. So we'll start off black set, empty, gray set has T, white set, all of those objects as we had before. All right, our final state. Black pulled T over, which brought X, which in turn brought Y and Z. Gray set goes empty, and the white set would have our ingredients. And so the garbage would be the eggs, flour, and cream. Right, when groceries was set to null, we lost our way to get to our first node in the list. And from losing the first node in the list, every other node in the list is also no longer reachable. Does the tracing make sense? Right, it's kind of like the 5 degrees of Kevin Bacon. If you take Kevin Bacon out of the mix, then nobody knows anybody. Okay, let's go ahead and we'll take a 5-minute break. Who's Kevin Bacon? Yeah, so let's go ahead and take a 5-minute break. Well, we chuckle at the only good joke I may have had the entire semester, but you know. And then we can, let's see, yeah, then we'll go over the test. I'll unmute for a few minutes and then we can swing back. Okay. Let's see what we got here. Shapes, right? Star graph. Let's see if it's bipartite. Bipartite means we need to be able to split into two sets. Let me get my annotations here, right? So start with A, see what connects to B, so B has to be in the opposite set. B connects to E, so it has to be in the opposite set, so that's fine. B connects to C, opposite set, and B connects to D, opposite set, right? So there are no edges between either vertices in this first set. And the second set only has one edge, so that's bipartite. And it's complete bipartite because B connects to every other vertex in the opposite set. Let's see. Right, it's just a smaller star graph, so those apply, no cycle, no wheel. Not a complete graph, just double check. I managed to grab two, basically the same question, so we'll see. I'll probably just give 2 points across the board on the test. Let me write that down so I don't forget, because I asked the same question twice, more or less. That's not something I intend to do. Where is Notepad? Okay. Okay. Number 3. All right, so it's not a cycle graph, not a wheel graph, not a star graph because we don't have anyone central here. All right, we got degree 1, degree 2, degree 2, degree 1. Check on this being bipartite or not. D goes to C, C goes to B, and B goes to A. So we can make this as bipartite, but that's not complete. So it's just a bipartite graph. All right, degree 3 across the board here for everyone. So it makes it a complete graph. And it's also a wheel graph. And it's just a matter how you want to redraw this. We got A connects to B, A connects to D and C. And everyone has a degree of 3, right? So a W4, everyone has a degree of 3, and a K4, everyone has a degree of 3. So it gives us a wheel graph and a complete graph. Right, everyone's degree 2, cycle graph, so it's not a wheel, not a star, it's not complete. Check to see if it's bipartite or not. If they were even, it would be, but because it's odd, right? A goes to B, B goes to C, C goes to D, and then D goes to E, and E also has an edge to A, so that doesn't let us get down into any of the bipartite scenarios. All right, check our degrees. We got 1, 3, 3, 3, and 2. All right, so not going to fall in a cycle, wheel, or star or complete scenario. Check our bipartite again. E goes to D. D goes to B and C, and B and C connect, so we're not going to have any bipartite. That, so that goes into the 9 above. All right, the wheel graph. And wheel graphs are highly connective, so we're not going to fall into any of our bipartite parties. cycle graph, and it's a complete graph, and it's odd cycles, so it's not going to be bipartite. Adjacency lists. All right, so A should have B and C in it. B would have A, C, D. C has A, B, D. D has B, C, and E. And E has D. All right, so ABC is correct. B has A, C, and D, so that one's incorrect. C has ABD, this has ABD but in the wrong order, so that's not correct. BCE and E should have D. So those three entries should be enabled. Most common degree of vertex in the wheel graph would be 3. Degree of vertex in a star graph, unless it's a star 2 where they both have a degree 1. Everyone has a degree of 1 except for the center point in a star graph, so that's none of the above. Right? It seems people know the answer here, but they hesitate for whatever reason for putting none of the above, because it's a rare exception for every degree to be the same in a star graph. The more common scenario is every degree has a degree of 1 with the exception of just one of them. All right, center of a star graph is B -1. And average cycle graph is 2, so that's not the above. Average complete graph, everyone -1. And we have Kruskal. And a nice big image. Okay, so let's, which edges cause a cycle before them and are specifically removed. All right, so get our 1s, get our 2s, get a 3, no cycle just yet. So we got a 4 here. So that causes a cycle. So AH is going to be an answer. Am I missing any 4s? No. All right, so we got 5s. Cycle, 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 and we get to our 6. So we now have our spanning tree. Everyone's connected, so we're done. Let me write that down to the side. So make sure we have AH. We have BC, CH, and GH. So AH, BC, CH, and GH. First 4 nodes after A. All right, so we have 3 options starting at A. First one to be added will be G. Second one to be added will be B. And then our third one to be added will be H. And then our fourth node to be added would be D. So we have GBHD. G, B, H, and D. All right, so every vertex in here is even, so that means we have an Eulerian circuit to start. Now, let's see the Hamiltonian. Can we create a path where we go from A to B to C to D to E to get back to A? Yes, we do. So now we have Eulerian circuit and Hamiltonian circuit. All right, Euler Hamiltonian. 3, 3, 3, 3, 3. So there's no Euler going to be there at all in Hamiltonian. All right, A, B, C, D, E, D, get back to A. So the Hamiltonian circuit. The correct rows in our graph. All right, so yeah, the image is a little bit big. That's for sure, but let's do one vertex at a time. All right, AB is 2, AG is 1, AH is 4, so A is good. All right, B should have a 2, 3, 5 in it for A, HC, AHC, all right, so C thing's got 3, 5, 8, 5 for BDH, B 585, right? So it looks like we have a problem here. C to D is saying it's H. C to D we have here. So row C is bad. Along D 381. Where are we at here? D. So we got the right numbers 3, 8, and 1. D, E, H. So that's all lining up. E is 3, 6, 7. I don't see 3, 6, 7 here for E, so that is wrong. F says it has 6, 8, 2. Get 6, 8, 2, so double check. Right values, right? E is at 6. G is at 8. That's G, and H is at 2, so that's good. G has 185. Get the right numbers. 1 to A, 5 to H. 1 to A, 5 to H. F saying 8, so that's correct. And then H. Everyone's nice and populated. So it's just a matter of 435 for ABC. 435 ABC. 1725. 1725. All right, so we have those two rows that are messed up. All right, breadth first search starting at D. All right, so D is our first output. Breadth first search. We're going to go ahead and NQ A E N G. So go ahead and go to A. Correct ones. Oh yes, thank you. I did invert that, didn't I? All right. Yeah, try to pay attention to that in case anyone inverted. Let me know if you inverted the answer like I just did. If you make the same mistake as I do, then you get credit for making the same mistake. All right, back to, all right, so A gets pulled off. All right, so we know about A, G, D was initially. So B gets NQ'd. E gets pulled off. And that tells us about F and H. G gets pulled off. That is our fourth vertex. Now we got to work our way to the last one. So B tells us about C. F tells us about I, and I will be the last one after we process through that. A. Yes, we started at D. A, G, and I. Depth first search starting at G, or D, let's speak correctly. 1, right? So we have 3 options, A, E, or G. So we go to A. 1 option at this point. 2 options, we go to C. 1 option at this point. 2 options, we go to E. 1 option, G is before I. And lastly there. So second output was A. Fourth output was C. And lastly is I again. Disadvantage of being later in the alphabet. All right, this one, I'm not looking for any particular answer. Just however you want to address it in the context of data structures should be good to go. All right, so at a minimum, you want some lists. All right, so and I'm in some lists to represent guests, all right, items, menu sort of thing. All right, that's just going to check our raw data. But other things to associate, right? We start building some groups. So, you know, an adjacency list for the carpooling situation. All right, so Abel's bringing Bryce, Charlie, and David. So you have Abel as the head of the list, and then Bryce, Charlie, and David are all riding with Abel, sort of thing. 6-1, half a dozen other apples, oranges, pears. It's more of a thought exercise for looking at things. Oh, looks like I have a goof in my key somewhere. Let's see. Oh, looks like I was giving 2 points back anyways for number 2 because the key's just completely wrong. Make a note there. Key wrong for number 2. All right, so I need to give points back by fixing the key for number 2. And I'm just giving 2 points to everyone because I duplicated my question anyways. Using a bipartite graph work for the, yeah, bipartite graph would work as well for the food items. So you have the people and then what they're bringing, right? Because you might have multiple people bringing desserts, depends on how categorizing, right? So if you're categorizing main dish, appetizer, dessert as the food, right? Multiple people can be bringing an item, and some people might be bringing, someone might want to bring rolls and dessert. So yeah, a bipartite would work. Yeah, so for number 2, I need to fix the key, and then you'll get points added in to that for that. Plus, I'm going to be just adding 2 points for duplicating a question. Star and the bipartites should be what I put as the answers here are correct. What I put on the key is incorrect. All right, this is an S3. Remember, star graphs go all the way to S1. I've mentioned that's kind of ridiculous to go to S1s, but some authors say you can do that, so we accept it here. I wouldn't use a bipartite for carpooling because that could actually, I suppose that could work, right? Because we have Abel on the left set, and then Bryce, Charlie, and David on the right set, and then you have Ethel, and Francine and Gavin in another car, Ethel being the driver, and Francine and Gavin in the other set. Yeah, that could work too. And all of a sudden, if someone needs to change, you change the association from right now. All of a sudden, Francine is jumping into Abel's car because they got a big car, different timing, or whatever the story is. So you could use bipartite there to maintain that data relation there as well. Okay, let's say the high score cell was 88%. I was looking at this earlier. Yeah. So when I fix the key here, you do not lose points. So if you got full credit on number 2 already because you saw the same things that I saw when I made the key, then you're still good. Grade correcting, I choose the additive option, so you'll only add points to whatever you got there. Yeah, so if you chose the opposite for number 19, I'll try to pay attention to that after I grade the test and I didn't correct that. Please message me then and I'll double check. And number 2 is the only one. I believe that's the only one. Oh, look at that. Looks like I have an issue with number 4 as well. All right. W4. Just double check. Triple check. All right, yeah. So it looks like number 4 also has a bug. Bugs, there's always bugs in the machine somewhere. Yeah, it's possible you can get up to 4 points back from key errors, and then I'm gonna give everyone 2 points when I get around to grading it, just because of me having a duplicate question on the test. It wasn't entirely duplicate, but it's close enough. Any other questions about the answers or the graphs in general? We'll see questions like these again in 5 weeks. 18 Euler and path. Right, so in order to be Euler, everyone has to be even. To be a circuit, or up to 2 can be odd for a path. And we have 4 vertices with an odd. Right, A, B, C, and E all have a degree of 3. So we won't have anything Euler in that. The final is on everything, going all the way back to stacks and queues and all that comparatively easy stuff now that we've been getting deeper and deeper into the woods. Yeah, for the Thanksgiving question, we've got a holiday coming, and I don't want to put code on this test. You have to do very, very little in your response for the Thanksgiving question to lose points. So even if you're using a non-optimal data structure for the solution, is not relevant. It's not part of the grading criteria. The grading criteria is, did you address this problem from a data structure's perspective? And that's basically yes or no. And if it's yes, did you spend time to actually process and analyze it, or just take a bowl of spaghetti and dump it on there and say, look, there's a bunch of lists. Sort of how the grading works for that one. Yeah, well, being Thanksgiving night is just an event with people and people bringing food. It's a potluck, effectively. The fact that it was Thanksgiving isn't particular. It's just because of the time of the year. Thanksgiving being what, 10 days away? Used Dijkstra's algorithm for number 22. I'll have to see what you put in your answer to see what you did for Dijkstra. You can certainly use Dijkstra for figuring out who's going to carpool. I can see that works as a good solution. Dijkstra, routing problems and shortest path is certainly a good way to apply the figure out who's going to pick up whose situation. Okay, let's swing over to program 4, just doing a few weeks. Right, this is certainly going to be the most code, program 4. The root of this program is a hash table. Right, it's the very first line. This is the key thing here, right? Go dig up your singularly linked list code, or go dig up, if you did the adjacency list exercise, go get your adjacency list exercise lab code, bring it over here and rebrand it as a hash table. And that's a big chunk of the purpose of this program. We're going to be using the hash table to store variables for our little interpreter here. It's going to store the variable's name, what the state of that variable is. It's 1, 2, 3, 4 sort of thing. And whatever other associated you want to hold on to it as well, scope, whatever you want. All right, so when the user declares variables, you add to the table. When they want to use variables, you read from the table, sort of thing. All right, programming language is called Borg. It's just an arbitrary name. There are not very many keywords in the language. It's a very, very brief language. All right, instead of curly braces, we have start finish blocks, so you don't have to worry about looking for curly braces. Single line comments, variable declarations. And this number 4 might be the more difficult part to do, variable expression, because the expression is a little bit more complex. All right, mathematical operators, increment, decrement, plus those good things, and printing. All right, so let me swing down to the sample program and swing back up. All right, so you're going to give the program a text file, or you can ask them to repeatedly type lines of code. Either way, it's the same difference. Interpreter doesn't need the whole program listing to actually execute the code. Each line is going to fall into one of two categories. Either the first word on the line, so go back to program one, which was using splitting based off of a space character. You're going to want to use your input code from that for program 4 to break each line apart and check the first word. If the first word is a comment, you can just ignore the rest of the line and carry on. Read the next line, it's also a comment. Ignore the rest of the line, carry on. And we got a start block. All right, so start just indicates a block of code. Blocks of code identify scope. All right, so we'll check a scope has been created. Var borm equals 25. So first word on this line, just like on the start and the lines before, is a keyword. Right? In the case of var, we know the next word is going to be a variable name. Then it's going to be assigned to a variable value. So we'll take that name, create an entry in the hash table with the value 25 associated with it. Yes, this Borg language is our language. It is our interpreter language. We're creating an interpreter. This interpreter interprets, quote unquote, the Borg code programming language. Right? Same thing, most of these lines of code, the very first word is a keyword, and then there's going to be a very limited syntax after that. If the first word is not a keyword, then the first word on a line is going to be a variable name. And even with our increments, we still space to separate all these things out. So exact same code that you're using, or for most of you that you use for program 1, remember the reverse Polish calculator, you read a number or an operator, and then you did things. And there's white space delimited single white space character. In the case here for our code, and then feed it to an engine. All right. Swing back to the language for a second here. Errors. All right. We'll get to that in a second. So back to the hashing. Our hash function. All right. We're just using our character folding. Fold our letters on top of each other. That plus adding in the multiplication of the more or less the index in the array. So 1 based indexing. A is the first position. 65 is the value of A in the ASCII table. We're going to go table, multiply that by 1. Add in 66, which is the value of B. It's the second value in the variable name. So we multiply by 2. And then same thing for C, 67 times 3. Of course, modulo table size. So let's talk about the interpreter, right? So the interpreter, let's just do it this way, string array lines equals. Comment or x equals 5 and print x. Right, so we're going to be getting our array lines, either you're doing array lines repeatedly or you're reading all the lines from a file. And we want to break the line into parts. Right, so whatever code you're using, sort of thing to break a line apart, you just want to look at that very first part. Right, case, let's say we're just going to do print. And we'll just print a message, console, right line, printing. In case var, it's gonna be the same idea. Kill my data. Declaring a variable, which means we want to go ahead and get the name, add to the table. Yeah, this is just C#. I'm just trying to show you a mock-up of how the program would more or less work. Right, so we read a line of code, identified that we had a var. You see there's more space here. All right, so I didn't put anything for the comment, so nothing happened for that line. We had var x equals 5, so it's okay, we're declaring a variable. You need to get the name x, add that to the table. Right, the variable name x, which has been parts 1 in this code here, and the parts 3 would have been the value. And then we got to a line of code that said we need to print something. So get that. And then see one thing. Last thing we do, x equals 5. All right, so our default case. And we just go ahead and say we found a variable. Some variable logic. Right, some variable logic. So this is effectively what the core of your engine is going to be. Why are you giving me red squiggly? So annoying. Oh, really? It's complaining about my comment? Okay. Right, so when you start this program, don't go try to take the sample program from the description here and then try to create an application that's going to work on this nested scope, all that jazz. That's a lot to try to do for one program from scratch to finish in one go. So what you want to do is something similar like this, or even smaller. Right? That's possibly even too much code. Var x equals 5 and then print x. Right? This is a good starting point to develop the program. The ability to recognize the line of code that causes you to add a variable to your table. And being able to process line of code that can pull the data from your table. Right, so it's just a matter of creating your hash table. Right, chained hash table. Right, add string name and data sort of thing. Public int. All right, whatever, look up. String name sort of thing. All right, so I'll just go ahead and put in something here so it actually does something. Let's see. String int. All right, so this is just some basic code. Do not want to go based off of this. A tuple is just a name value sort of thing. So I can just have a string and int together as a type. It's just creating a type for me. In fact, let me not do that. Let me just create a variable class. Public string name, public int value. And let's keep this less C#y. Variable. Name equals name and v data value where that is equals data. And we can add V. All right. R 0 less than values length count. There we go. Do. All right, wasn't that liking about my lookup? It likes just fine. Okay, red squigglies. All right, so let me go ahead and create my chained hash table. That's fine. You're close. All right. Plus table that lookup. My parts sub one of things. I mean, things are working according to plan. Otherwise, we're adding table add parts sub one and parts sub 3. Not a lot of very strong code in here, but try and keep this in a rapid prototype. Yeah, program 4 is going to look more or less like this, assuming I don't have any bugs. All right, so it printed 5. All right, so when we get to the var port, declaring the variable, got the name, added it to the table, got the value, added that to the table, and then we got around to printing it. It printed out 5. Right, so you actually need to make a chained hash table. At this point in time, I don't actually have a chained hash table. I have a single chain where I'm just dumping everything into it. So that needs to be an array of linked lists. And I'm not using linked lists, I'm just using a list type just to keep the example quick. But this is the foundation of how you want to approach the problem. Right, and feel free to hard code your sample code to start, or if reading from a file is not working well, just go ahead and read from the console. Right, being able to get the data into the program is not intended to be a roadblock or a wall or a pit trap, but a lot of people's ability to read from files isn't the strongest because it's not a common thing you do very often, and it's one of the areas of programming courses that doesn't tend to get a whole lot of time on it either. And quarter of the time I find myself Googling how to do the IO myself for reading from a stream in .NET, even though I've done it probably 100 times over the last decade or so. It's still not often enough for me to remember which of the stream readers and text readers and all the fun stuff that I want to work with. Right, but just an if stream is all you need. Just read from the console, do your read lines, all that good stuff, and that's pulling the handbrake on what you're trying to do. Just skip reading from a file and just read from the console. And if you want to skip reading from the console, just create an array of strings and just iterate through that. At some point, we're getting the logical, more or less state that we're iterating through line by line of code that we're interpreting. That's just an array of strings. How we get the strings into the application logic and work with your table is the lesser concern. Biggest concern is get your chained hash table and you just try to get declaring a variable and printing a variable up and running. And then once you've got that working, then you can start folding in the other language capabilities. Questions at the moment? Okay. All right. That's our time for tonight. Any other questions about anything else at the moment? No, this is in the Files tab on Canvas. No. I don't put. Yeah, so when you lose a scope, that's when you delete from the hash table. Yeah, so next week after people have started to digest this program a little more, we can add to this a little bit. Just make sure you're on the right track for addressing scope. Yeah, adding variables together, things like that. All right. Well, I'll keep floating around in case you start cracking on this or have other questions. But otherwise, there's no more lecture for tonight. Go ahead and go on mute, and I'll stop the share unless someone has a question where I need to bring it back up.